Question 7, which is a moments question. We've got a beam with length 5 and mass 25 kilograms, so it's worth bearing that in mind. The beam suspended in equilibrium in a horizontal position by 2 vertical ropes, and they're shown in the diagram. And then we're told that a particle of mass 60 is attached to the beam at B. So I'm going to attach that on now. And it has a mass of 60, so the weight is 60 g. And it remains in equilibrium in a horizontal position. Beam is modeled as a uniform rod, and the ropes as light strings. So it being uniform means that the weight is going to act in the centre, and the weight is 25 g. If the whole thing is 5 metres, then that would be a distance of 2.5 metres from A. And we also know that there's 0.5 metres between B and C, so the distance between the centre of mass and C is 2 metres. So in the two strings we're going to have tension forces. They're going to be different tension forces, or they might well be different, so we'll label them TA and TC. So this is our complete diagram. The first question says, can we find the tension in the rope at A and the tension in the rope at B? So in doing this, there's two things that we can do. First thing I'd be tempted to do is to resolve all the forces. This might actually find something for us, or just give us a useful equation. So we'll resolve the forces vertically. I get the two vertical forces, which are the tension forces, both going up, and they're equal to the downwards forces, so 25g and 60g. So I know that the two tension forces summed together will give me 85g. Now, that hasn't solved anything for us, but it is a useful equation to perhaps use later. So now what we can do is try and find out one of the tension forces, and then we can find the other one. And we're going to do that by taking moments. Now you can pick any point you like to take moments about, and in this particular question there isn't really an advantage of doing one point over another. So why don't we pick A? So we'll take moments about A. And if I take moments about A, that eliminates the force at A, TA. So I'm going to eliminate TA, and basically going to be looking for the force TC. Taking moments about A means that the weight is a clockwise moment, and so is this particle at the end. And TC is an anti-clockwise moment. So if this whole thing is in equilibrium, which we are told, then the clockwise moments are going to be equal to the anti-clockwise moments. So the clockwise moments, 25g, and we're going to multiply by the distance, which is 2.5. Another clockwise moment is the 60g, and that's the full distance, which is 5. It's equal to the anti-clockwise moment, which is tc, times, and that's going to be 4.5 as a distance. And if I rearrange all of that, I can put these bits into the calculator, divide by 4.5, that gives you a tension force of 789 newtons. And I can put that back into this equation up here, and I can work out what TA is then. So TA is going to be 85g minus TC, and that's going to give you about 43.6 newtons. So those are our two tension forces for part A. Part B then asks us to consider a different situation where particle P is removed and replaced by particle Q. So this is what the picture will look like. We've got a rod, we've still got your centre of mass here, and we've got a new particle here which we're going to call a weight mg, because the mass is now m. And it's still going to be in equilibrium, we're still going to have a tension force here at C. Now, what's going to happen is if we put a really big force down here at the point B, what would start to happen is the string at A would go slack and it starts tilting around this way. So we have a sort of situation of tilting. If we want it to remain in equilibrium though, it's on the point of tilting. So if we're on the point of tilting, we can say that this tension force here doesn't exist, but there'll still be a tension force here at the point C. But just to simplify the whole thing, what we can do is take moments about C. So if we take moments about C, we'll have a anti-clockwise moment which is 25g times, and this distance here is, as before, it was 2. And that's equal to the clockwise moment, mg times the distance here, which is 0.5. So if we rearrange that, we can find out what m is. M is 100. So that's part I. And part II says to find the greatest tension. So I should mention, find the greatest possible value of m. Now the greatest possible value means as much weight as we can put down before it starts to tilt. Yeah, so before we are no longer in equilibrium. So that's on the point of tilting. The greatest possible tension then, we basically work with this value of m and say that the forces up are equal to the forces down in this particular case. So Tc as a force up should be equal to the two forces going down. And now we found m, that's 100g. So the greatest possible tension is going to be 125g, or 1230 newtons.